Aaron's got on here the volume formula, which is good. So we got 1/3 power squared h, right? So similar to the volume of a pyramid, which is 1 the area of the base times height. Well, a couple of things I just want to show on here. I know Aaron knows it, but in case we're not seeing some of the things, we give it a diameter of diameter of 6 centimeters. So that implies the radius is, right, it's half our diameter, which is 3 centimeters. Okay, so this is where Aaron is getting the 9, which is really 3 squared. So we got 9. Sorry, not a fan of this format.
See, I just kind of skipped it, so I thought I'd put the step in.
Oh, I know you like it because it saves space. That's why you like it.
That's what I do.
So we cross reduce. We actually get 3 here. So I'm going to continue to work over here. So what we really have is 67 over 3 pi is equal to h. And then we get h is equal to, once you do that, h is equal to 7.14. Okay? So if the original question was to find, second one, surface area of the cone, hopefully you recognize that eventually you get down to here, you get to L. Solving for L, we're missing the height. Okay, so this could have been a lot harder question just by giving you B. Okay. But hopefully it steps you through a process where that once you start figuring out surface areas, so in this example, what Veronica was doing, here's a formula, pi r squared plus pi RL. So again, she got r squared is 9. Then pi times 3. Okay, so we put any numbers in between things. We have brackets as well, so we're just separating, making it clear what's going on. So 3 times pi times L. And here is, well, we don't know what L is. We don't know what the slant height is. So Veronica nicely goes off to the side and says, well, here's our equation. Missing a square root there. So 3 plus, and that's where it's obviously goes, oh, I'm not given the height. I'm given the radius, I'm given the height. And that's when all of a sudden you start panicking. They're like, Mr. Tam, you didn't give me the height. How can I prove it? It's like, well, wait a minute, well, what else have we given you? Right? We give you a diameter, so it applies radius. Then all of a sudden, well, you give me the volume. Maybe I can do something with the volume. And that's one thing I've noticed, that in the homework, we come to a cross-set question you guys don't know, I see a question mark. I don't even see an equation on it, a formula. It talks about surface area, it talks about volume. If you write it down, it's okay, well, I'm given the volume. What do? You write it out. 1/3 power squared. Oh, h. Oh, wait a minute, there's an h there. Maybe I can get h for my volume. So just by simply writing it out, you actually see the formula, you might draw some connection there. So Veronica goes off and calculates L based on height. Well, she got 7.10, which is fine. Going off, and her slant height is 7.70. Plugging back into the formula, and eventually we got a surface area of 101. And what's our units? Centimeters squared. So unfortunately, Veronica, I'm going to take off a half mark for technical for not reading. It's in there. Alright, any questions on this? Okay. Hopefully you're finding out from this unit. I mean, some of us getting our homework done, which is good, because it's so much straightforward, right? Here's our formulas, determine what measurements we need to plug into our formulas, and it's mostly calculated. So today we're going to talk about, I didn't bring a ball with me. We're going to talk about spheres. So one thing I want you guys to do, to start us off, is give a definition of a sphere. I mean, most of us conceptually knows what a sphere is. Like it's sultry. I try to describe what a sphere is. So in terms of geometry, in terms of mathematical, what you need to understand, especially once you get into three-dimensional geometry, probably in grade 11 or 12, right? In order to see what's going on in there, you need to understand what we're talking when we talk about relationships. Okay? So a sphere is actually a relationship. You know how we talked about y equals mx plus b? Right? That's a relationship between two variables, x and y. Eventually you get into mathematics where you actually deal with relationships with three variables. X, y, and gives you the third variable. Z, right? Or z. Right? Now you're dealing with a three-dimensional world. So what a sphere really is if you take, let's say, a pen. Okay? So this is sort of like my radius. And so the bottom of the pen is my center of my sphere. It's as if I took this radius and I went all around an infinite amount of times. And what we're doing is, you remember how we had the equation line y equals mx plus b? We're plotting points all along. Well, this is what really a sphere is as well in mathematical context. There are an infinite amount of points based on this equation, given our center and this length, all around this three-dimensional space. And after you plot all those billions and billions and billions of points, what kind of figure do you actually see? A sphere. Okay. So that's what sort of mathematically what a sphere is like. And once you get to the equations, dealing with equations of a sphere, that's what it sort of means. Okay. So specifically, we want to talk about volume. So I'll have on here the volume described on there. And here is, I'm not going to go off and prove it. Mr. James actually found some tennis balls to do with his class. I didn't have time to set it up. He did this good demonstration of tennis balls and a little canister that the balls come in. So he does something with that to demonstrate that the volume of a sphere. So if I had a ball, I'm trying to show off a ball. The volume of a sphere is 2/3 of the volume if I took that ball and made a cylinder around it. So in other words, the cylinder would be exactly as high as the ball and as wide as the ball, but it's just a cylinder. So it fits in. I think anybody play racquetball? Squash, no squash. The balls are a little bit small, but racquetballs they used to sell in single cans, right? And you only buy one racquetball at a time. And what happens is a can fits that ball exactly in terms of the width is exactly as wide as the ball, and the height of the can is exactly how tall the ball is. Okay, so that would be a nice demonstration. But what happens if you wrap that cylinder around that sphere, you calculate the volume of that cylinder. The volume of your sphere is actually 2/3 of that volume. Okay, that's how it comes about. So that's sort of like the long explanation of this equation. So the volume of a sphere is actually 2/3 the volume of a cylinder. So imagine if you can that cylinder wrapping your ball paper. Well, this is just equals to, if my sphere, so pretend this is a round object, right? If this is my diameter, right? What is the radius? Well, half of it is half of it. So we know that diameter goes 2r. But how high is my cylinder then? How high is the cylinder that I need to put to encapsulate that ball? Yeah, it's the same as our diameter, right? So we want to put this ball in a cylinder exactly. The height of our cylinder is exactly how big our ball is in terms of its diameter. That's right. Well, let me get there and let's see if it's a different one. Okay. So we realize the height of the cylinder is equal to two times the radius as well. Okay. So we're gonna get this magical cylinder. What's the volume of a cylinder again? What's the volume of a cylinder again? Well, of our base. Yeah, area of our base, which is just a circle, pi squared, and we want to multiply by the height. Well, in this case, how high is our cylinder? Yeah, it's just our diameter, right? This is what I'm filling in on your sheet right now. Well, what is the diameter? What do we know the diameter to be? Well, the diameter is over here. What is that in relation to our radius? 2 times the radius. So it's just 2/3 times pi r squared times 2r. Well, I'm going to simplify this. Get rid of all my numbers. Simplify my numbers. Well, what's 2 times 2? That's just 4. So we're left with 4/3 pi r squared times r now. Well, we have r squared times r.
R cubed.
Yeah, it's just r cubed. Really, the formula for the volume of the sphere is 4/3 pi r cubed. So that's how we sort of derive it then. Once we know that the volume of the sphere is just 2/3 the volume of that cylinder that holds that sphere, holds that ball. So is this a formula you know of, Brian? So let's do a couple of quick examples. So volume is equal to 4/3 pi r cubed. Well, this one we just plug straight in the radius. Not even exciting. You can do this in your calculator, just 4 times pi times 4 to the power of 3. So we'll do what Aaron says. We do 4 to the power of 4, which is 256 pi
4 to the power of 3.
over 3.
4 to the power of 16 times 4.
Well, but then I have multiplying times 4 as well, right? So it's really 4 to the power of 4. Does everybody know where the power button on the calculator is? What it looks like? So there's an x with a y to the top. Okay? So that means x to the y. So if you go 4, hit that button 3, you should get 64. Because that means 4 to the power of 3. Multiply 4 again, we get 256 times pi divided by 3, so 268.08. Okay, second example is the same thing, except what's tricky about this one?
It's height.
You talk about height, well really, we don't talk about height of a ball, really diameter. Well, what's the relationship between diameter?
Radius times 2.
So if it's not confused, even if you don't, it's like, well, I'm not given the radius. Don't know. That's what sometimes I see in our homework, right? Well, you're not giving me the radius, I don't know. Write down our equation. V is equal to 4/3 pi r cubed.
How did you get 4 to the power of 4? Like there's 4 over 3. So. Oh, because you multiply by 4, that's 4 plus.
Because here I got 4/3 pi, 4 to the power of 3. Well, I can multiply, I could change this to just be 4/3 times 4. Right? The order of my multiplication doesn't matter. Right? So what's 4 times 4 to the power of 3? So that's just 4 to the power of 4 pi over 3.
Then what would we do for this height? Because the radius is 3, so 4 times.
So here the radius is, so r is 3. So the volume is 4/3 pi. So here I can't do the same trick because it's a different number. It just happened that my radius was 4.
Okay.
But what I can do, yeah, I can cancel, right? 36 pi.
Wait, why do you cancel the 3 of the power cube?
Because this is really 3 times 3 times 3. I have a 3 is on the bottom, so I can cancel one of the 3's. So it becomes 3 squared. So instead of 3 to the power of 3 becomes 3 squared. Question?
Do we have to like change the formula for everyone, or can we just plug it in?
Yeah.
Change the formula.
Like, not change the formula. Just like we have to cancel stuff out. Or
No, you can. If you don't want to cancel, that's fine. All that allows me is I can do the math in my head now. Because now I got 3 squared is 9 times 4. Now I know it's 36 pi. 113.10 centimeters cubed. Okay? Any questions, A or B? Kind of straight. And again, so Abby asked a good question. Well, she would like to plug that onto her calculator, right? How many buttons do you have to press on there, on your calculator? Well, you have to do 4 times 3 to the power of 3. A lot of button pressing. My fingers are fat. These buttons are small. Easy to make a mistake in our calculator sometimes. So that's why I want to do less work with my calculator as possible. And this is why I reduced. Because once I got this to be 3 squared times 4, well, I know 9 times 4 is 36. It's a lot easier for me to punch in 36 times pi on my calculator to get this answer. Find, well, it's supposed to be given the volume V, find the radius. So basically here, we want you to rearrange our. Okay, so listen carefully because I think the homework touched on some of these questions and some of you didn't know how to do this when it came down to the volume of a cone. So here's our equation for the volume of a sphere. What the question is saying that, well, if you're given the volume sometimes, and that's what stuff does. Oh, I'm given a volume, I don't know what to do now. But given a volume, you need to find the radius. I mean, how many variables are in this equation?
2, 1, 8, 3, 1.
Well, here 1. What's the one variable?
Oh no, never mind. In this one, 2. Volume 2.
There's two variables, right? Volume and radius. That's all we need to know. So if you know one, you can get the other. So the question here is that if we know the volume, how can we actually get the radius? So in other words, what are we doing to this equation? Isolate. So this goes back to our equations unit way back. We rearrange the formulas a bit. We're isolating for what variable this time, I think? Yeah, isolating for r. So how do you get r by itself here?
Divided by square root of 3 pi.
Well, for first step,
Square root. No, because the square root's not. I mean, cube root. Square root's a cube root.
so we might want to do cube root, which might be a new terminology. But before we do that, we need to get that r cubed by itself first.
Okay, divide by 4 over 3 pi.
So divide by 4/3. What's another way of saying that, really?
Multiply by 0.
Yeah, well, let's multiply by the reciprocal. So here I'm going to multiply by the reciprocal. So by doing that, that sort of gives rid of my fraction. Now I'm left with 3/4 v put a pi r cubed.
Divide both sides by pi.
Yeah, pi is just a number. Okay? Bless you. It's not a variable, it's just a number. So that's something we need to remember. It's just a number. So we divide both sides by pi. So we get 3v over 4 pi. We put the r cubed. So now that we got r cubed by itself, yeah, so there's this function or routine or talk about cube root. I'm divided by pi. So what that looks like, a cube root is the same symbol as the square root. Yes, but with the 3 in here. That's on the calculator. I'll show you how to use it in a second. So what we get is r is equal to the cube root of 3v over 4 pi. So here's the question. If we're given the volume 50 centimeters cubed, find the height. Well, because we're dealing with sphere, let's write down our equation. R cubed. But this point, we're given the volume. So given the volume, chances are, what do we need to find? We're given the volume, what is it we're going to find it? Radius. So we'll rearrange our equation to over here. So we got R is equal to cube root of 3v over 4 pi. So that's cube root of 3 times 50 over 4 pi. So I can reduce this to be, so R is equal to the cube root of 75 over 2 pi. So that should be, which is very different than what I just got. So 75 divided by 5 is cube root of 11.94. I reduced because I got 50 and 4. I just reduced that to 25 over 2. I like reducing my fractions.
Is that 22? I don't know what number was it 4 before. And then you cross reduce the 50 and the 4. So you got 25.
Yes. I always like to simplify my fractions because it makes my arithmetic simpler. Yeah, we're gonna get there. So has everybody got 11.94?
Yes.
Okay, and yeah, I forgot the cube root on here. So on your calculator, there's a button that sort of looks like. Oh, I actually have a cube root button.
We have like a little square root with an x and a y.
Yeah,
A small x and then a y. Yeah.
You just do like.
And then you just, once you press that, then you press 3.
So on your calculator, you might have there's actually 2 ways of doing this. On your calculator, you might have a symbol that looks like x, y.
Yeah.
So is it
No,
doesn't,
it's y. It's the x and y.
oh, it's the y that's, so like that? Okay, just wait. So if you have that on your calculator, that means you put in 11.94 first, hit that button, and then hit 3 for your x. That means there's a cube root. Yes. Okay. So yeah, some calculators don't even have the y. Other calculators might have something that looks like this, which is what mine does. X 1 over y. Okay, that means the same thing. You'll learn that in grade 11, exponents. They're called rational exponents. That's the same thing. So you have a button in your calculator that looks like that. That means the same thing. So same thing, you put in 11.94, hit that button, and then you hit 3. And you should get 2.28, 2.29. What's the question asking? We want the height. Right. So therefore the height is 2.29 centimeters times 2, which is equal to 4.58 centimeters. Okay. So we need to remember to answer the question at the end. That's right. And you need a better calculator. Maybe your calculator too. Okay, so here's another question. Deals with volume. So let's do this one really quickly because it's a little bit tricky. So volume again is 4/3 pi r cubed. So we want the volume of in orange. So this is 4/3 as pi. Well, the height is 8 centimeters, so that makes our radius 4. And we just had this answer before the last time. What was the answer? What's 4/3 pi times 4 cubed?
Gotcha.
Was it like 256?
Well, we just did the
What? 268.08 centimeters cubed.
268.08 centimeters cubed. Okay? So now you know the volume of an orange. So the question is, well, given a box with these dimensions, 40 centimeters by 30 centimeters, and then a height of 30 centimeters. So we're going to stack oranges in this box. So the first question is, how many oranges would this box hold?
That's by the volume of the box.
Well, does it fit nicely? The oranges fit nicely?
No, you have to have more than one.
Well, if you look at, well, okay, just even we take a top view of the box, right? So we look at a box like this. I know where you're going at this, Matt. You're just thinking, well, we calculate the volume of the box, divide by the volume of the orange, we get how many oranges we get. Not quite. Well, we don't know. But this is a box, right? We put an orange in here. Is there gaps?
Yeah.
Right?
Is that a cone?
It's an orange.
No, it's a cone. It's a sphere. It's orange.
No, I meant like the borders.
So the- So the question is, if this is 40 centimeters long and 30 centimeters wide, how many oranges can we just even stack in one layer? Well, how many oranges can we fit down here? 30 centimeters.
So that's the height.
3.
With a lot of room.
Well, 3 back-to-back oranges is only 3 times 8 is 24. We can't quite fit a fourth orange in there, right? Only needs a 6 centimeters. How about across? How many can we fit across?
No. 5. 5 perfect.
Yeah, it'll fit 5 perfectly, right? Because 40 divides, or 8 divides into 40 by 5 perfectly. So how many oranges can we fit into one layer?
3 times 5, 15.
Yeah, so we have 15 oranges in one layer. While the box is 30 centimeters high, how many layers can we actually have? So we have one orange sitting on top of another.
45 oranges.
No, 5. 5 is 3 layers, 30 times.
So how many oranges can we stop one on top of the other?
5, because 8 times 5 is. Never mind. Oh, sorry, I was looking at length.
Right? The height of our box is 30 centimeters.
So 3.
So really the same over here, right? Same as our width. We can only get 3 layers. So we can only fit 45 oranges in this box. So here's 15. Well, how much empty space would be in the box then? Well, how do we actually calculate that? Yeah, so we just find the total volume. So it's almost like if this box was filled with water. And then we figure out how much water is in there. Then we put the 15 oranges in, and then we calculate how much water fell out, right? How much water fell out, what's that equivalent to? Yeah, because you put to the volume of our oranges. And then we're left with, well, how much water is in the box? So that's another way to kind of look at this question. So really, how much space is in the box is the volume is equal to the volume of the box minus the volume of our oranges. Right? That's how much volume, how much space is in our box, so to speak. So I call it the volume of air. Well, what's the volume in the box? What's your equation for volume of the box? What's the volume of oranges?
268.
Yeah, so I'm going to calculate that first because I get a little more space. So the volume of oranges is really 15 times each orange takes up 268.08. So that leaves me.
How's it 15?
Oh, sorry, not 15, 45, thank you. 45 times 268.08 is 12,060. So here I just plug in 12,000. So length is 40 times 30 times 30
You get 36,000.
minus 12,060.
You have 36,000.
36,000?
Minus 12. When you
36,000
you have to minus.
minus 12,060. And what do you get from that? 23, 940.
But that doesn't make sense because you can still fit another 12,000 in there.
Wait, Mr. Tam, why couldn't you do it like this? The volume of the box divided by the volume of the oranges to get the number of oranges you can fit in the box.
Because then you're assuming that there's no gap. Right? That the oranges all fit perfectly one beside one another and you have no gap. Right? But you know that we visually do that with oranges. Like we put spherical things into a box, you're always going to get a gap.
So
Right? Like for example,
Wait, is this
even-
how much would the box could? It's not how much could the box potentially hold. It's how much the box will hold.
yeah.
well, but the question is how much empty space is there in a box? I mean, that's what the actual question is. How much empty space is in the box?
So there's more empty space. Than
So what Matt discovered is
More empty space.
this is more empty. So is this an efficient way to hold our oranges? No. Right? Well, first of all, what's one thing that we could do? We could shorten our width and we could shorten our height. Right? So we could actually make the width a factor of 8. So either 32 or 24. Same thing with our height. Right? Well, think about another way. Is this an optimal way to actually pack the oranges? A bag? It's pretty hard to cart a bunch of bags around and stack bags. You need a bunch of crushed oranges. Well, when you put, and then I should, next time I'm going to bring some balls from my other class, but if you put two balls together, it's the optimal way to stack balls one on top of another.
You make like a pyramid.
Well, basically, you got 4 balls together, you get this nice little crater that you put in the ball, and then it actually will fit a lot better. So that's a whole other area of math that companies have to get into is what's the most efficient way to pack like 24 balls, right? Because we talk about materials, you know, it costs money to make this box, especially if you're gonna make 1 million of them, 2 million of these boxes, right? You save plastic, so it's an environmental thing, it's a cost thing. It's almost a science. All right, one last thing, I want to take this up really quickly. So we'll talk about the surface area of a volume as well. Just going to give you the equation. Surface area is 4 pi r squared.
4 pi.
So in other words, what's the relationship between the surface area of a sphere and sort of I took that sphere, I cut it in half in the area of that circle. What's the relationship? What's the relationship if I have, let's say, an orange, right? And the surface area of this orange, so in other words, the orange peel, what's the relationship between that, and if I took this orange, cut it completely in half in the area of that circle that we see? Yeah, 4 times, right? So really, this what we're saying is 4 times the area of the circle. So it's almost 4 times the area of the of the area of the circle that's in that sphere. So that's one way you can try to remember it. So let's do the diameter first. So examples. So this was just straight plugged in 4 pi r. So what's our r value in this case? Right, diameter is 6. So that implies that the radius is so 4 pi 3 squared. So that's equal to 9 times 4, 36 pi. 36 times pi is 113.10. Okay. So same thing with this question, surface area, 4 pi r squared. Guys, Tyler, do you want to move back that corner, please? This is not working out. So 0.75 squared. You need to round up because the next digit is 8. Okay, not two boring examples. So here's a more interesting one. So the surface area of the ball is 254 centimeters squared. What is the radius? So surface area. Okay. So just write down a formula if you're confused where to go with this.
Isn't it 4 pi r squared?
Oh, sorry, 4 pi r squared. Look at the circle.
Okay, you will find.
Well, what's the surface area? Are we given the surface area?
It's 254.
So just plug in the numbers. 254. And now, what is it that we want to do, Matt?
Square root.
Not yet. We need the r squared by itself first, okay? So what is it that we need to do to get there? Yeah, so we divide both sides by 4 pi. So r squared is equal to 254 divided by 4 divided by 5. It's 20.21. So take the square root of both sides now. You get r. And you get 4.50. So therefore, radius is 4.50 centimeters.
Yeah, I've heard it before. If it's what about it?
Usually, yes. That 5 seconds won't tell you. Ooh, much harder question. A balloon is blown up to have a radius of 8 centimeters, right? So blowing, getting this balloon bigger and bigger until it gets a radius of 8 centimeters. What's the diameter? 16. So now we want to add 2 more liters of air, right? So my lung capacity is about, I don't know, 16 liters? I have no idea. No, that's a pretty huge lung capacity. So I blow another 2 liters of air into the balloon. Well, what change in the surface area do we have now? In other words, how much bigger did the balloon get versus the surface area?
We need to know how much a liter affects the area.
Well, let's just start from the beginning, right? What surface area? Right, we just asked for surface area. 4 pi r squared. What do we know r? It started off at 8, right? We added another 2 liters. So if we start off at 8 and I put in 2 liters of air, is my radius still going to be 8? Did the balloon stay the same size? No. So it's simple. What the heck?
We don't know how much bigger
don't know how much bigger it gets. Well, but given the radius that it blew up to, what can we find out about the radius of that? So if you already got blown up to a radius of 8 centimeters, what is it that we can do with that? Once we know the balloon is 8 centimeters, that's a radius of 8 centimeters. What is it that we can do with that when the balloon's at that stage? The diameter, which is 16, but that doesn't really help us. Well, what is it that we're talking about? We added volume to the balloon, right? So can we figure out the volume at 8 centimeters? Right? So let's figure out the volume 8 centimeters. So at 8 centimeters, the volume is, well, what's the volume? 4/3 times pi times cubed. So what's the volume there? So 4 times pi times 8 cubed gives me 6433 divided by 3. So my volume is 2144.66 centimeters cubed. Woo!
Now, how much is that? What's a liter is that?
That is 2.14466 liters.
How'd you get that, Colin?
I used a unit converter.
Yeah. Okay. Well, what hopefully you remember from last class is 1 centimeter cubed equals to how many milliliters?
1.
Yeah. So that one's easy to remember, right? So how do you get to one milliliter?
1,000.
Sorry, 1 liter is equal to 1,000 milliliters. So in order to get from, so this is really 214,466 milliliters. And we need to divide that by 1,000 to get 2.14466 liters. Okay? So that's what Colin has said. So that's how many liters of air is in that balloon when its radius is 8 centimeters. Well, I haven't most ways. Especially since I did the conversion from milliliters to liters. Well, what do we know now about the balloon? So at 8 centimeters, so the radius 8 centimeters, it has this much volume. Yeah, so we just blew in another 2 liters. So we're going to add 2 to this. And now we get 4.14466 liters. So at the end, this is how much air is in our balloon. So now that we know the volume of this, so I'm going to convert this back to centimeters squared. So I'm going to move it back. That applies 4144.66 centimeters cubed. So I know the volume. If I know the volume, what can I find out? The radius. So now we're starting to get to figure out what this R is. So before we get there, I'm going to erase this. We go up here and say, well, R is equal to the cube root of, somebody help me out? I don't remember what I did with the slide. So R is equal to the cube root of 3 times 4.144.66 over 4 pi. So R is equal to cube root of 3 times 4.444.66 divided by 4 divided by pi. So we should get the cube root of 989.46. So R then is, for Veronica, since we can't figure out how to do it in a calculator yet, 9.96. Yeah. Well, no. Now we have the radius. We didn't need to we didn't need to know the original surface area, did we?
Yeah.
What?
So you have to do
Oh.
what's the surface area.
Are you serious? I hate math.
No.
I think we should just give up.
I have the answer if you want it.
That's a good one.
Well, question. Is it really that hard?
No.
It's just
It's just too much.
It just is a lot of work.
Conceptually, it's not that hard. Once we got there, it just requires effort.
What is the change in
Who has that
Can I put on
about these days?
So what does it change? So we do need two surface area calculations.
And subtract.
We're gonna do that on another page. So what's the surface area?
Surface area equals 4 times pi r squared.
So I'm gonna call this surface area 1, what we started off with. So surface area 1 is 4 pi, radius was 8.
Yeah.
So that is 4 times 8 times
804.25.
That's 804.25,
I got 8.25.
right?
You want to
Then we would need the surface area at the end, which is 4 pi r squared again. And what was our r value?
9.96.
9.96?
Yeah.
Thank you. Right? I mean, once you got to here, it's not so bad, right? Just plug in a bunch of numbers in a calculator. 4 times
Oh,
Five.
it's 124.
496 squared. 1,200, 200. 46.60.
I got 5.8.
Probably because you did.
I did the actual.
Yeah, that's fine.
All right.
So the total, the surface area delta was that symbol. You guys remember that symbol? Yeah, delta. So the change of surface area is surface area 2 minus surface area 1, which is 1246.6 minus 804.25. And that's equal to
442 point something.
442.35.
I got 0.33, but I think that was just because I was
So
off.
therefore, a change in surface area So change in surface area is 442 point. Like my therefore statement?
Yes.
Unless we start using math symbols, you can take shortcuts. How'd I get what? Well, 4 times pi times 9.96 squared. It's 9.96 times 9.96 times pi times 4.
That's last week, they were doing how to try
That was our radius that we did way back up here, right? After we blew it up, after we added 2 liters of water. I'm sure 2 liters of
Library.
Iron Friday. Yeah.
So the 9.96 came from here, Andrew. And let's change this to
Could we just get rid of one whole page?
Like
Of
the
course
second
you
one.
would.
Why does it say
Like,
one?
one to say never mind.